Hello friends, welcome again to engineering tutorial. Now in my previous video I discussed about the load line analysis of bipolar junction transistor and the concept of operating points in a bipolar junction transistor. So in today's video we will discuss about the operating regions of a BJT or the modes of operation of a BJT, the ways in which a BJT operates. We will discuss about that. So let's get started. So first is the operating points or the operating regions of a BJT. Now in short, a BJT has three ways in which it operates, and it is defined by these 3 points, that actually 2 points in one region. Okay, so first is the cutoff point or the cutoff mode of operation of BJT. The second is the saturation mode, and the third is the active mode. Okay, a BJT can operate in one of the following 3 ways: the cutoff, the saturation, and the active mode. And these are marked by the 2 endpoints, the cutoff and saturation point, and the active region which occupies the space between the cutoff and saturation point. Okay, so don't get confused by this. We'll slowly move into it so that you understand this entire operating mode of BJT in a better way. Now, before we discuss about the cutoff, saturation and active mode of operation of BJT, we need to understand a bit more about the internal structure of the BJT. Now this is the schematic symbol of a bipolar junction transistor. You know that this arrowhead is the emitter, this one is the base, this one is the collector. Now this is the BJT in block form. It consists of 3 blocks with a p-type block sandwiched in between either 2 n-type blocks or an n-type block sandwiched in between 2 p-type blocks, okay, forming NPN or PNP type transistor. Here we have taken the NPN type transistor for analysis. So if you pay attention to this, only this much of the portion, you will see that it consists of an n-type block followed by a p-type block, okay, which is the emitter and the base. So this emitter base block combined together, don't neglect this one, okay, do not think about this, just consider these 2 blocks. So it can be viewed as a PN junction diode, isn't it? This 2 blocks, emitter and base, okay, this is a PN block, PN junction diode block. You can visualize it in that way. Similarly, if you neglect this block, cut it out, neglect the emitter block, just consider the base and the collector block, okay, this p-type and n-type block. So again, this much of the portion, okay, this much of the portion, neglecting this emitter n-type block, it can be viewed as a PN junction block or a PN junction diode. So you can say that a bipolar junction transistor's internal structure can be represented as 2 PN junction diodes connected back to back. First one is the emitter base PN junction diode, the second one is the collector base PN junction diode. So in a way you can also say that the internal structure of BJT is composed of 2 PN junction diodes connected back to back. So you can represent the internal structure of BJT in this way. This is the base terminal, this is the collector terminal, this is the emitter terminal. Now this PN junction diode is the collector base PN junction diode, which involves the collector block and the base block, the p-type base block and the n-type collector block. Similarly, this PN junction diode involves the base terminal and the emitter terminal, the p-type base terminal and the n-type emitter terminal. Okay, so in a way you can say that the internal structure of BJT consists of two PN junction diodes, okay, the collector based PN junction diode, the emitter based PN junction diode connected back to back. The collector based PN junction diode is also called as collector diode, and the emitter based PN junction diode is also called as emitter diode. Now these two diodes determine in which mode the BJT operates, whether it operates in cutoff mode, whether it operates in saturation mode, or whether it operates in the active region mode. Okay, these two diodes play an important part in that. That's why I made you understand this whole two diodes connecting back to back thing, so that you understand the operating modes of BJT in a better way. Okay, now let us first discuss the cutoff point. Okay, now for the time being, just ignore this first point and the third point. Just ignore that. Focus on the second point. When we reach the cutoff point, or when can we say that a BJT is in cutoff mode? Okay, a BJT is said to be in cutoff mode when both the emitter and the collector diodes are reverse biased. A BJT is said to be operating in cutoff mode when both the emitter and the collector PN junction diodes are reverse biased. It means both the diodes are off or both the diodes are open circuited. Okay, then we can say that the BJT is in cutoff mode of operation. Okay, this is the cutoff mode BJT internal structure, where both the diodes are open circuited, they are off. Okay, you see this, both the diodes are open circuited, they are reverse biased, they are off. As a result of that, in cutoff mode, all the BJT currents are equal to 0. The base current is 0, the collector current is 0, the emitter current is 0. This is the cutoff mode of operation. Now I will explain the first and the third point at a later stage, so please have some patience. Next, so this is the cutoff mode of operation, where both the PN junction diodes, the emitter and the collector diodes, are reverse biased, they are off, they are open circuited. As a result of that, all the BJT currents, terminal currents, are 0. Next we have is the saturation point. Again, please ignore the first and the third point. I will discuss them all together at last in the BJT output characteristics and load line that involves some of that. So I will make you understand that at last. So focus on the second point. The BJT is said to be operating in the saturation mode when both the emitter and the collector diodes are forward biased. Okay, when both the emitter and the collector diodes, the PN junction diodes, are forward biased, the BJT is said to be operating in the saturation mode. So in the saturation mode, both the PN junction diodes are on or short circuited. So the internal structure of BJT is in this form. Okay, this is the normal way in which the BJT looks. And in saturation mode, both the diodes are short circuited. Okay, so a short circuit path is created. As a result of that, the collector current becomes equal to the emitter current, which is only applicable for the saturation mode of operation. Okay, the collector current is equal to the emitter current because of the short circuited PN junction diodes, which creates a shorted path from collector to emitter terminal. As a result of that, the collector current becomes equal to the emitter current. Again, this is only applicable for the saturation mode. Okay, so this is the saturation mode of operation of BJT. So in cutoff mode, both the diodes are reverse biased, off, open circuited, like this. In saturation mode, both the diodes are forward biased, on, and short circuited, like this. In cutoff mode, all the currents are 0. In saturation mode, the collector current becomes equal to the emitter current, which means that the base current is 0. Okay, the base current is 0. Now, finally, the active region. I said previously that the active region is the region between the cutoff point and the saturation point. All all the space which is occupied between the cutoff point and the saturation point is the active region. Now in the active region, the emitter diode, the emitter based PN junction diode is forward biased, and the collector diode or the collector based PN junction diode is reverse biased. Okay, the emitter diode is forward biased, which means it is on, it is short circuited, while the collector diode is reverse biased, it's off, it's short circuited, it's open circuited. Okay, the emitter diode is forward biased, it is on, it is short circuited, the collector diode is reverse biased, or off and open circuited. Now in that case, this relationship is applied. IC is equal to beta IB, where beta is the current amplification factor. Now please again pay attention that all these things we are discussing about the common emitter configuration of BJT. Okay, common emitter configuration of BJT. That's why this beta thing comes into play, because beta is the current amplification factor for common emitter BJT. Normally the common emitter BJT is the most popular configuration which is used for a variety of purposes, mainly for the purpose of amplification of weak signals. That's why we are using that common emitter configuration in all these videos, the common emitter configuration. Okay, so in the active region, IC is equal to beta IB, this relationship is applicable. Okay, this is the internal structure of the BJT. IC is equal to beta IB in the active region. Now in all the saturation, cutoff and active region, I told you to ignore the first and the third point. Okay, so now you will understand what is that first point and third point which I was telling you to ignore. Now here in the cutoff point, let's first go into that. In the cutoff point, we say that the cutoff point is marked by the point where the load line intersects the IB equals to 0 curve. Now again, I have discussed about the load line and the operating points in a separate video. So please check that video in my YouTube channel and then come to this video, otherwise you will not be able to understand many things. So please check out that video related to load line analysis of transistor, where I have discussed about the procedure, how to draw a load line and concepts about operating points. So please check out that video. Okay, so the cutoff point is the point where the load line intersects the IB equals to 0 curve. Now let's see where it is. Okay, this is the output characteristics which is drawn for the common emitter BJT configuration. Now if you remember, I have already discussed about it in the common emitter BJT configuration in my separate video in my YouTube channel. So here the plot is drawn between the output voltage, which is the collector emitter voltage, and the output current, which is the collector current, at constant input current, which is the base current, for various values of base current, starting from 0 up to IB equals to IB saturation. Now this IB equals to 0 at the bottommost plot, while IB is equal to saturation is the topmost. So this point where the load line joining the points VCC by RC and VCC, which intersects this IB equals to 0 plot, okay, this plot, output characteristics plot, this point is the cutoff point. Okay, the cutoff point is the intersection point of the load line with the IB equals to 0 plot. Again, at the cutoff point, the value of collector emitter voltage is nearly equal to VCC. This value, this point, at this point the VC value is nearly equal to VCC. Now I'll say that this VCC value is far away from here. It is because, for the sake of clarity and your better understanding, I have taken this point a bit far away. In actual life, this point is very close to this point. Otherwise, if I would have shown this point very close to here, it would have been very clumsy and you would not be able to understand that. So in real time operations, if you plot and determine the value of collector emitter voltage at cutoff point, this point will lie very close to VCC. It will be very difficult to actually separate and distinguish between these 2 points. Here, for the sake of clarity, I have taken this point a bit away from VCC so that you can see these 2 points separately. Okay, the collector emitter voltage value at cutoff point is equal to VCC. Okay, this was the third point. Again just again for a recap, the cutoff point is the point where the load line intersects this load line. The blue line is the load line which intersects the IB equals to 0 output characteristics plot, this bottommost plot. This intersection point is the cutoff point. Next is the saturation point. The saturation point is that point where the load line again intersects the IB equals to IB saturation curve, which means the topmost curve. Okay, so this point where this blue colored load line intersects the IB equals to saturation, this plot at constant IB saturation value, this point is the saturation point. Again, at saturation point, the collector current value is nearly equal to VCC by RC. Again, this point is a bit far away, is generally deliberately taken a bit far away from this VCC by RC points, because for the sake of clarity, so that you can understand these 2 points in a better way, if when you plot it in real time, in actual conditions, this point will be very close to this point. So I have deliberately taken it a bit far away so that you can distinguish these 2 points. Okay, so the saturation point is the intersection between the load line and the output characteristics plot at IB equals to IB saturation. So this is the saturation point. Again, another important thing, at the saturation point, the collector emitter voltage value is equal to the knee voltage. It is called as the knee voltage. Now, if you can remember, I have discussed it in the common emitter configuration, that the knee voltage is that value of collector emitter voltage beyond which the collector current becomes constant and becomes independent of the collector emitter voltage. That is, beyond the knee voltage, any increase in VCE has no impact on the collector current. It becomes independent of VCE, a flat curve. So this is the collector emitter voltage value at the saturation point. It is called as the knee voltage. So here, this is all about the operating points on the characteristic curve. Now, the active region. The active region is the entire region between this saturation and cutoff point. Okay, this saturation point and this cutoff point, all the space in between these 2 points is the active region. All the regions below that and below this is the saturation region. Okay, everything to the left of this, everything to the bottom of this cutoff point is the cutoff region, everything to the left of this is the saturation region, and all the space in between this cutoff and saturation point is the active region. Okay, so this is the active region in between the cutoff and saturation point. This region below the cutoff point is the cutoff region. This region to the left of the saturation point and upwards is the saturation region, and all the space in between this is the active region. Okay, so now you are clear about the cutoff, the saturation, and the active region or modes of operation of a BJT. So here we have discussed about the various operating regions or operating modes of a bipolar junction transistor. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to electrical and electronics engineering. Have a great day. Thank you very much.